Hello everyone, welcome to this advanced pre-stress concrete design course. Now we are in the module 1, the first week of the module. Now in this part of the video, we will talk about the pre-stressing strand, which is the steel, and then how to determine the mechanical properties of pre-stressing steel and how different types of strands are produced. We will spend some time on that. So, the expected learning outcomes, the student should be able to discuss what are the various types of pre-stressing steel that are available, and then the student should also be able to understand and describe what are the essential mechanical properties of pre-stressing steel, particularly the stress strain curve behavior, and discuss the production process of pre-stressing steel. Pre-stressing steels are produced in a different way that we will spend some time, and the student should be able to discuss that after going through this video. And we will also talk about long-term effects of pre-stressing steel. Basically, pre-stressing steel undergoes relaxation, so we will see what is relaxation. Briefly, we discussed it in the previous module, but we will see how to estimate the loss that is happening from relaxation. Then we also have Ramberg-Osgood model. That's one stress strain curve model. How to develop that model based on the test data so that that can be used for design purposes. So, these are the expected learning outcomes. Now, there are various forms of pre-stressing steel that are available, and wire is the most fundamental unit of pre-stressing steel. And pre-stressing wire is typically a single unit made up of steel, and you get wires in different range of diameters starting from 2.5 millimeter, 3 millimeter, 4 millimeter, 5 millimeter, 7 and 8 millimeter. Depending upon the element and the size of the element, even individual wires can be used of a suitable diameter. For example, if you look at sleepers, people tend to use even individual wires and do pre-stressing. Now, what are the different types of wires? You can see here that the steel wire, to improve the bond, either you can have a plain steel, pre-stressing steel wire, or I can have a three-sided deformed shapes. Basically, the indentation is given so that it is going to have a better bond with the concrete. Now, you also have this kind of a oval shaped, four-sided oval shaped indentations are made on the around the diameter of this plain wires. So, then it becomes indented wire. So, in plain wire, as the name says, it does not have any indentations and the bond is expected to be less. In an indented wire, you can have a circular, elliptical, various patterns of indentations can be put on the surface of the wire during the manufacturing process, and this is expected to have better bond, because finally we need to have a very good bond with the concrete. So, this indented wire is expected to have better bond with the concrete. Now, pre-stressing steel properties are usually, if you look at IS 1343, it is discussed in section 5.6 and in section 18.3 of IRC 112. Now, you can see different types. As we said, the fundamental unit is a wire. We have plain cold drawn stress relieved wire, and we have indented cold drawn wire, and we have high tensile steel bars are available, and then we have uncoated stress relieved strand is available. We have uncoated stress relieved low relaxation strand. This is typically what commonly used. Okay, low relaxation strands. We will talk about that. This is the most commonly used, and it should conform to this IS 14268. So, the code gives you what are the specification, what should be the chemical composition, and what should be the minimum mechanical property, what should be the minimum percentage of elongation. All these things are given in this standards that are listed here. For example, for this low relaxation strand, which is commonly used for pre-stressing, we have to resort to this IS 14268 for making sure that the wire or the strand that what we are using is conforming to the standard specifications. Right. Now, we will also talk about how these pre-stressing steels are there. I can say wire, we have discussed, it ranges from anywhere diameter from 2.5 to 8 mm are available, and you also have plain wire or indented wire. The indentations can be of different shapes that we have discussed in the previous slide. Then we have strand. Now, strand is basically a group of wires, right. So, usually we use the 7-wire strand, which is very common, but if you want more prestressing, 19-wire strands are also used, but 7-wire strand is commonly used, where you have a central wire and then remaining 6 wires will be braided on the central core wire. Then you get a very flexible prestressing strand, and prestressing strand can be wound into rolls of any length you want. So, that is again another advantage of prestressing strand, because they are by the virtue of their shape, they are very flexible, they can be rolled into any length. So, you can do prestressing from one end to another end of the building in post tensioning. So, we have discussed what is post tensioning in the previous modules. Then we have tendon. So, what is tendon? You can say group of wires is strand. Now, when I put multiple strands together, you form a tendon. So, group of strands or wires are wound to form a prestressing tendon. Typically, tendon is also said as an entire system. It is not only about the steel strand, you also have a protective sheathing, and then you have the anchorage cone, all those things, entire system is typically called as a tendon. Okay. Tendon can be made up of a single steel bar, or the diameter of the bar is typically much larger than that of a wire. So, we have seen it in the previous module as well. So, a tendon is actually a group of strand, and it is typically used for high force applications. Now, you can say what is cable? Now, cable becomes a group of tendons. Now, group of wires is strand, group of strand is tendon. Now, group of tendon is called a cable. So, they form a prestressing cable like the one that you see here. You have so many tendons can be grouped together, or so many strands can be grouped together to form a large cable. Now, let us spend some time on production of 7-wire strand. Okay, as I have told you, the 7-wire strand is the most common form of prestressing steel that is typically used in prestressing applications. Let us see how it is done. So, first what we take is, we take the round plain hot rolled non-alloyed high carbon steel rod, and then we do the descaling and cleaning process. So, it undergoes the some mechanical abrasion and cleaning process. That is the first step. Then what we do is something very important process called patenting. Patenting is nothing but giving a heat treatment to this plain hot rolled round steel bar, and then what we do is we heat it about 800 degrees centigrade, then we cool it down slowly to make the metallurgical structure very homogeneous. Okay, that is a patenting process. Then what we do is we take that of a particular diameter, and then we do the wire drawing. So, what is the meaning of wire drawing? We take that larger diameter and we pull it through dies of successively smaller and smaller in size, so that the size of the wire will become smaller. So, when it is undergoing through this pulling process, basically the metallurgical microstructure improves greatly and you get very good strength. So, that is the process of wire drawing. Now, once the basic wire is formed, then we do something called stranding process. Now, what is the stranding process? We spin the 6 wires over a central wire, like I told you, 7-wire strand. You will have one wire which is a central wire, and then remaining 6 will be helically wound on the top of the central wire. That process is called as stranding. Next, we undergo, in fact, after stranding the process is calm. Then depending upon how you do the later stages, you have 2 types of strand. One is a stress relieved strand, another one is a low relaxation strand. In stress relieved strand, we take the strand and then we heat it to about 350 degrees centigrade, and then we cool them slowly. So, this is called stress relieving, because when you pull it through dies of successively smaller diameter, you also develop lot of residual stresses. So, by heating it to 350 degrees centigrade and allowing them to cool slowly, what we are getting is we are relieving all the stresses, the residual stresses. That type of final product is called stress relieving. Now, we have one more type, either you do stress relieving or strain tempering. What is the meaning of strain tempering? So, after stranding process, if you are again heating it to 350 degrees centigrade, but while you heat it, the strand is also kept under some minimum tension, like what you see here. Okay, the strand is always kept under minimum tension. So, you can say that while you do the heating process, if you apply some nominal tension, that process is called strain tempering. Again, you get better mechanical properties, and also you tend to have low relaxation, which we talked about in the previous module. What is relaxation? Again, you get a superior product. So, let us put it that way. Right. So, this is the thing. So, what is the stress relieved strand? Stress relieving, as you said, we heat it about 350 degrees centigrade. We are actually, by doing this process, removing the residual stresses due to cold drawing, and which results in higher proportional limit. So, when you know stress strain curve, you know that higher the proportional limit, then even if I up to that stress limit, if I remove the stress, there will not be any residual strains, right. So, if you have a material with higher proportional limit, which is good for you. So, that is what we do. We heat it to 350 degrees centigrade and then cool down slowly. Now, in low relaxation strand, we do strain tempering, which is an effective in improving the stress strain characteristics, and it has an additional advantage of reducing the time dependent loss due to relaxation of strand. So, now again we have discussed what is a relaxation strand. This strand actually acts like a rubber band, you stretch it, right. So, you stretch it like this. So, you apply some force, right. So, this is, let us say, strand. Okay. Now, this is your force. Okay. So, this deformation, the length, this remains constant. Typically in pre-stressing, you tend to stress it from one anchorage zone to anchor zone, or in pre-tension system between the two anchor heads, you do the stretching, right. So, that means the strain remains constant. But what is the force required to keep the strain constant? What will happen is that will not remain constant. The force required to now keep it at constant strain will keep coming down. Or in other words, force divided by cross section area is your stress. The stress required to keep the strain constant in a pre-stressing strand will keep coming down. So, that is called as low relaxation. The strand tends to relax. It will not require the same amount of stress, but the stress required to keep it at same strain will keep coming down. So, but that is not good, that will lead to loss of pre-stress, because again the amount of stress multiplied by area will give you force. That is the same force we are putting it on the concrete. Now, the force that I am putting it on the concrete, if it is coming down, then the performance will be compromised. So, that is the reason. So, when you use low relaxation strand, this relaxation losses will be very less compared to that of stress relief strand, and this is the nowadays commonly used, okay, commonly used, right. And here again, as we explained in the previous slide, we heat it to 350 degrees centigrade and cool slowly under tension. So, here not only you are heating it, but you are heating it under tension. So, with this the limit of proportionality will be further increased, and that is better for you, because higher the yield strength, the better it is for you. So, we will explain that in the stress strain curve. So, you can see here, if I plot the stress in the y axis and strain in the x axis, you will find that these are the deformed rebars, the high strength deformed rebars. You take 415 or for example, let us say this is roughly about 415, right. You get little bit of plastic portion depending upon the process again. This may not be there also for high deformed steel rebars, right. And then typically you fail at about 15 to 20%, okay. This is for normal deformed reinforcing bars. Now, if I take high strength bar, which is also used, okay, what we have is roughly about 900 megapascal or so will be the strength. Again, then you get this will go about 1100 or so. And then, but what you see here, so it is going to fail at a much lower strain, about 9% or so, right. Of course, these numbers are very tentative. Nowadays, you have ductile steel as well in rebar that can go 20-25% strain also, right. So, but what we are saying is, when you make the strength higher by some production process, your yield strength goes up, your ultimate strength goes up. However, the strain at which it is going to fail is going to come down. This is 16, this has become 9 or so. So, roughly 50% of reduction is there between deformed reinforcing bar and high strength bar. Similarly, if you go to 7-wire strand, which is the most common form of prestressing steel that I have told you, you said due to this drawing, the wire drawing processes, what happens is your yield strength goes up significantly and your ultimate strength also goes up. So, this ultimate strength is roughly about 1860 megapascal, okay, and yield strength is roughly about 1620 megapascal, 1600 or so, 1600 or so. Megapascal, right. So, you get very high yield strength and ultimate strength, but again if you look at it, this strand is going to fail at about 6%. Now, when you say why strain in percentage, if the actual strain will be 6 by 100 for this, which is going to be 0.06. But for rebar, if you look at it, the strain will be 0.2, 0.18 like that. So, that is the strain at which it is going to rupture, right. So, for our design, typically we take the yield strain. So, this as my yield strain, right. So, that again we either take 0.2 percentage or 0.1 percentage proof stress as your yield stress, right. Okay. So, the moral of the story is higher the strength, lesser your strain at failure, okay. Lesser will be the strain at failure. So, you can see 7-wire strand, it is failing at about 6% strain, which is 0.06, right. So, epsilon u is 0.06. Okay. This fact you have to keep in mind. Another important aspect is whether I take 7-wire strand or high strength bar or deformed bars, the elastic modulus, which is the slope, let me say P, which is always close to 200 gigapascal, be nearly same. So, whether I take this green color or the red color, everything is 200 gigapascal. But if you look at concrete, higher the strength of the concrete, higher will be the elastic modulus. But steel, though you get strength higher, but elastic modulus does not change. They are nearly 200. In fact, for high strength steel, the elastic modulus is expected to be slightly lower. Typically, we take 195 or 196 gigapascal as your elastic modulus. So, higher the strength, lesser will be the strain at failure. The elastic modulus does not change, yield stress goes up, right. So, these are the things that we have to replicate in our design calculations. Now, what are the difference in stress strain curves of pre-stressing steel? You can see here, stress strain curves or pre-stressing steels are induced by how they are produced, okay, what kind of treatment they are subjected to. So, this figure shows the variation of 0.2 percentage proof stress for wires under different treatment process. We said low relaxation, stress relieved and so on, right. So, as drawn wire, if you look at it, the blue wire, which is this, right. So, this here this. So, if you look at the limit of proportionality for this case, you get only this, so which is lower, right, which is lower value. But stress relieved is better, so it goes somewhere here, and for low relaxation it goes as high as here. So, what you see here is, that is what we said, the limit of proportionality where it remains pretty much elastic, that limit of proportionality is going to go up if you do the treatment process better. So, as drawn, untreated wire will have lower limit of proportionality, and also, but the ultimate strength there is not big change, only this from limit of proportionality to the highest strength, it is taking a lower stiffness, right. So, it is going like this, so like this. So, at these strain values, if you can see, the stress that is offered by this untreated wires are less, but if you are using stress relieved wire, you get higher stress compared to this much higher, for example, this much higher, this much higher, and for low relaxations even it is higher. For a particular strain, the stress that what you are going to get in low relaxation, especially in this regime is going to be higher. So, which is better for you from design point of view. So, that is the reason we have to use low relaxation strand. So, the production process plays a major role on what is the yield strength and how the slope is changing. So, that we have to keep it in mind. Now, how the IS codes are addressing this stress strain curve behavior from design point of view. Okay. And these are the curves that are taken from IRC 112, okay, which is a bridge design code, and this is for untensioned steel. That means there is no, this is not a pre-stressing, it is a non-pre-stressed steel, non-pre-stressing steel. Okay. Now, you see here there is a black color curve. This is for a regular rebar. Okay. You get what is called as ultimate tension strength and what is called as yield strength, and typically we take at 0.2% proof stress, right. So, then we get yield strength. So, FIK is a yield strength, FT is your ultimate tension strength. This is an idealized bilinear curve. So, if I convert this green color into a bilinear curve with approximation, then it becomes an idealized bilinear curve. So, that is what we have seen here. So, this black color curve, that is what we talk about. So, you get yield strength, right. So, you get yield strength and you get ultimate strength and so on, right. Then this is with the hardening. So, this is with hardening. That means after yielding there is an increase in strength. This also can be idealized as a bilinear curve without any hardening. So, that is what here it is done, this red color curve, that what you see, and it goes like this and then you take like this. So, the stress strain curve of the actual curve can be either idealized as a bilinear curve with hardening response or elastic plastic response. So, this is an elastic plastic response. Yield strength remains same, but the FT also becomes Fy. So, you do not take that the hardened strength. Okay. So, this you keep that maximum strength only as Fik, which is your yield strength. Okay. These are the two idealizations. Now, we can also divide this by factor of safety for material factor safety, which is typically 1.15. We take gamma S is equal to 1.15, right. And then the same, the bilinear curve, whether with hardening or with no hardening, the entire response can be divided by gamma S to come up with again two types of curves, which is called as, okay, this is called as factored simplified by design bilinear. This is a design curve, right, and then factored idealized design bilinear. So, this is your factored idealized bilinear curve. Maybe so, this is your factored bilinear, idealized bilinear. So, you consider the strain hardening as well, but you can also have idealized simple curve as well, right. It's like this. So, what are the difference between this idealized bilinear and simplified bilinear? Simplified bilinear does not take hardening. The same, those two things can be divided by gamma S, but then gamma S the division will come only after this FID. Okay. So, let me go back. Okay. So, the yield strength divided by gamma S. Before that, before in this region, we do not apply gamma S. Okay. So, only after the yield strength we apply gamma S. So, you get, when you do that, these are design curves, these are called design curves. Okay. And these are idealized curves representing the actual material property, but when you divide it by partial safety factor for material, then you get your design stress strain curves. Okay. So, you get either straight simplified design bilinear or factored idealized bilinear. So, when you say factored, you are also dividing by gamma S factor, right. So, this is for again non-pre-stressed steel. Now for pre-stressing steel also we can do the same thing, right? So we go back again, right? We go back and the same curve, I can idealize like this, okay? And then either I can idealize like this or I can idealize like this, right? This is more conservative, of course, okay? So like this bilinear curve, this is for pre-stressing steel. Same way is what the code is saying, you can idealize like this, okay? In the same way, we have two types of idealization that are possible. This is your idealized bilinear curve, like what we said, and this is the maximum strength, which is your characteristics, and the FPK is typically taken as 1860 megapascal, okay? Now what is FP 0.1K? So 0.1K, as you can say, if I draw in the stress strain curve at 0.1% strain, that means at a strain of 0.1 divided by 100, which is 0.0001, and then I draw a slope. Wherever this fellow goes and touch in the actual curve, that becomes my yield strength, okay? So that's what we take that as a yield strength, because if you go back again to this curve, you don't get a very well defined yield point, right? So this curve, this is an ideal curve, right? So you don't get well defined yield point. So what we do is at 0.1 value, so you take this 0.1 value, okay, and you draw a line, straight line like this. Wherever this touches, that stress is called FP 0.1K. So that means I take at 0.001 strain, I draw a parallel line with elastic modulus, same elastic modulus as that of the original curve. Wherever it is going and hitting that stress, that's why it's called as FP 0.1K, right? Stress corresponding to 0.1% strain, which is 0.001 in this case. So that becomes your stress, yield stress, okay? So let's look at here. Now that's how we define this FP 0.1K, right? So you get your idealized bilinear diagram, okay? So then what we can do is this, how we get this is like this is actually yield, okay? Now the same curve for design applications, okay, I can now this is the actual idealization. From this idealization, again I can get two things, A and B. What is A? A is a factored idealized design bilinear curve. Again, what is the design curve? The moment we talk about design, the actual idealization has to be divided by partial safety factor. So that is what we are doing. For example, this point, it goes like this, that will corresponds to FP 0.1K divided by gamma s. Now again, what is gamma s? 1.15, right? And so there are two varieties. A is your factored idealized bilinear curve, or I can have a simplified, factored simplified design bilinear curve. So either I can take with the hardening or without hardening, right? There are two idealizations that are possible. Now you can see here epsilon UK typically values will be given to you, 2%, 3%, 4%, some values are recommended by the code. Now when you go to the design curve, again what we have to do is this epsilon UK also has to be knocked down by some factor which is typically taken as 0.9. So epsilon U or otherwise I should say epsilon UD is nothing but 0.9 times epsilon UK, that we will see it in the next slide. So the actual curve is idealized by a bilinear straight and hardening portion that is being divided by the partial safety factor to get two curves. One is the factored idealized bilinear curve or factored simplified curve. Okay, so this, when you use this factored simplified curve, of course your calculations are going to be conservative. Okay, so you are going to estimate it at a lower value. Okay, so that's, which is good. That's why the code is saying either you do simplified way or factored idealized design bilinear curve. Either way is acceptable by the code. Okay, Now with the example, let's see now how do we get it. For example, you see this is a curve that we talked about, right. So FPK, if you look at the standard IS 14268, if I am using let's say 15.2 millimeter, which is nothing but 0.6 inch strand, okay. If I take this 0.6 inch strand, and this is the maximum load at which it is rupturing, and the area of the 0.6 inch strand is 140 mm square. So you cannot directly put pi by 4 into 15.2 square, because these are 7 wire strand, right. So the entire area is not having steel. So there will be a lot of gaps in between them. So 0.6 inch strand is having a cross sectional area of only 140 mm square, but not pi by 4 into 15.2 square, okay. So when you divide that, you get 1860 megapascal. This is your ultimate strength, right. Now what is yield strength? So this is your FPK, right, FPK, which is 1862 in this case, right. Now what is FP.1K? That already we have discussed, which is your yield strength. Now how do you get your yield strength? The yield point is typically taken as 0.1% proof stress. That's what I said. You draw a parallel line to the elastic curve at a strain of 0.001, and wherever it goes and touches the actual stress strain curve, that you take that as your yield point. Or if you don't have the exact data, we can take FP.1K as 0.87 FPK. So that means 0.87 into 1860, this is going to be your FP.1K, which is your yield strength, okay. So that's the yield strength. Now what is design strength? Design is basically, again I have to knock it down by this gamma S. So I take 16,119 megapascal, I divided by 1.15, which is a partial safety factor, material safety factor, then you get 1409 megapascal. Now what is the strain corresponding to 1409? This typically, this modulus, as I have told you, EP, we take it as 195 gigapascal, slightly lesser than 200 gigapascal that we use for regular steel, right. So you take this 195. You know the stress, which is 1409. 1409 divided by 195 gigapascal will give me this strain. So this is nothing but your yield strain, okay. This is nothing but your yield strain, okay. So nothing but your yield, right, strain, okay. So this is the yield strain. So in this way you can get your this curve. So this is, what is this curve? Actually it is the factored, this is nothing but factored idealized design curve, which is the A that is given here. So this is your this. So you get this red color curve, which is your factored idealized design bilinear curve. What are the values you need? You need first FPK, and it should be typically, if you don't have value, you can take 1860 for a strand, and because that's the minimum that they should have. And then you take 0.87 FPK as your yield strength, which works out to be 1619. That 1619 you have to divide it by 1.15 to get your design yield strength as 1409 megapascal, and then your maximum strength you take that as your so this in the design curve, this is also taken equal to FP.1K. So this is nothing but your FPK 1619 megapascal, the maximum strength in your idealized factored design bilinear diagram. So you get all the values, right. So now that we know these things, this slope also can be calculated. This slope, you know, it is 195 gigapascal. Now you know this point and this point, and you know this strain. And how about this strain? Epsilon UK typically is taken as 0.02 by 0.9. So this value is also you can calculate. So you know this slope. So from in between those FPD and FPK, now that you know the modulus and you know the 2 points, at any intermediate points you can calculate the stress using this modulus, okay, this modulus, okay. So this way the entire factored idealized design bilinear diagram can be arrived at. Now this epsilon UK, now you can tell me, so how typically it is taken as, okay, this value is taken as 0.02. Okay. So, this epsilon EUD is epsilon EUD is taken as 0.02. Okay. This is the final maximum value. This is taken as epsilon EUK is typically taken as epsilon EUD divided by 0.9. So, it will become slightly higher, about 0.02 divided by 0.9. In this case, it becomes 0.0222, right. So, this way you can get your design curves that can be used in your calculations.